Hello everyone, my name is Hakan from Ruhr University Bochum. Today I am presenting our work titled Automated Extraction of Structural Elements and Section Views from Bridge Drawings Using Deep Learning. This research was conducted with Professor König at the Chair of Computing in Engineering. Bridges are critical components of transportation and require regular inspection and maintenance to ensure their safety. In recent years, digital workflows such as building information modeling have become increasingly important for managing infrastructure efficiently. However, many existing bridges were constructed before the digital era and are documented only through 2D technical drawings. These drawings include important internal structural elements like anchors, tendons, and section views. Manually extracting this information is very time-consuming and error-prone. Therefore, automating this process using artificial intelligence is a crucial step toward integrating older bridges into building information modeling and other digital asset management systems. Most existing research in construction field focuses on building layouts and external architectural elements. Few studies address internal structural components in bridge drawings, and to our knowledge, there is no existing method for automating the extraction of internal elements like anchors, tendons, section views, and their identifiers. This is the specific gap our work aims to address. On the right side, you can see a real bridge drawing from our dataset, and our aim is to extract specific information of different section views, like you see in the red rectangle, and also some information from the anchor and tendon elements, like you see in the orange rectangle, together with their specific IDs, like you see in the green boxes. We began with 71 real bridge drawings from German infrastructure projects, using 80% of them for training and validation and 20% of them for testing purpose. However, this amount of real data was not sufficient to train reliable models, and to overcome this limitation, we generate a synthetic dataset. And this dataset was produced by overlaying cropped symbols onto varied background drawings, also white pixels, with random rotations and placements. By doing this, we generated 1,800 images for section views, 500 images for tendon and anchor elements. Together, by combining 42 real train validation dataset drawings, we trained our models and then tested our test dataset. And the pipeline consists of three main stages. First, we apply deep learning models, YOLO version 8 or version 11 based on the best results. And then we detect tendons, anchors, and section views in the drawings. And secondly, we use OpenCV to locate rectangular ID boxes, which are usually positioned near the detected symbols. And third, Pytesseract is used to extract ID information from those boxes we previously described. And the final result is structured output like detected anchors, tendons, section views, and associated IDs. On the left side, you can see an example of annotated and cropped symbols for each class, anchors, tendons, and section views. Since the amount of real data set was limited, we had to use augmentation and with synthetic images. For this, we overlaid the cropped symbols onto background plans, applying random positions and rotations to create more variability. This process generated around 542 synthetic images for anchors and 542 for tendons and 1,842 for section views, all fully annotated in YOLO format. And for anchor and tendon synthetic data set, you can see here two different examples. The first one is one example from the synthetic anchor data set. The purple ones are anchor front sections, and the green ones are anchor longitudinal section views. So we randomly overlaid those symbols onto those background images. On the right side, you see a tendon front section view, section dataset, and the tendons are these small green circles, which are randomly then overlaid onto these background images. Here you see an example of section view synthetic dataset. As I explained before, there are 4 different subclasses, and for each subclass, it was again randomly overlaid onto white background, and we also used background images that were construction drawings, and then overlaid onto these randomly, and you can see that it's quite complex and it has very much information to it. The models were trained using YOLO version 8 and YOLO11 architectures using medium and large configurations. Image resolution was adapted to the size and detail of each element. Anchors were trained at 2560 to 3000 pixels and tendons at 3200 to 3600. And section views were trained with 640 to 1280 pixels, and all models were trained independently for 100 epochs using 8 NVIDIA A100 GPUs. After training our models, we tested them across 29 unseen test drawings. The YOLO11 large model produced the best result. Anchor detection achieved a high MAP score of 97%. Tendon detection reached 96%, and section detection was a bit more challenging with an average precision of 64%. Among the section classes, cross sections achieved usually the highest accuracy. After detecting the anchor and tendon elements, we performed shape detection using OpenCV to find out the ID boxes. And IDs are typically placed inside rectangular shapes according to drawing conventions. And after finding those specific location of those IDs, we used the same coordinates and applied Pytesseract to extract the text inside those boxes. And after testing this algorithm across 29 unseen drawings, the OCR achieved around 90% accuracy, but had some limitations due to some rotations and irregularity and a little bit noise inside those boxes. After finding the best models, we tested our pipeline. Here you can see an example of the test data set. As you can see, the images are quite well detected, anchors and tendons and IDs. Of course, there are some missing detections. On the low left side, you can see that these section views are not correctly detected. This drawing is actually a good example where most elements are correctly detected, but some ID boxes are missed due to rotations, as you can see here on the right side. And also here it's very small, but here is also some ID boxes missed due to the rotation. On the other hand, all of the section views are correct, and also the tendons and anchors are correctly detected. And here you see another example where longitudinal section is correctly detected, but some IDs are missing. For example, here, because it's a little bit rotated, the shape detection was not performed very well, and also there is a little bit noise on the shape itself. To summarize, we developed a pipeline that automates the extraction of internal structural elements from 2D bridge drawings. Using deep learning and OCR, we achieved high accuracy for detecting anchors, tendons, and moderate success for section views. Our results support the applications in digital model generation and bridge documentation workflows. In the future, we plan to extend the pipeline to handle different shapes, such as circular or elliptical IDs, and we want to improve the detection of complex section views and integrate the output into Revit or IFC-based BIM environments. Thank you very much for listening.